All right, guys, here I am with a example problem involving a thermodynamic cycle and a first law table. This one including an adiabatic process. So let's get to it. All right. In this problem, we're given a cycle, and we're given some facts here on the PV diagram. And specifically, we have three states. Oops, not P versus P, but P versus V, pressure versus volume. We're going to do our pressure in kilopascals this time, and our volume is going to be in cubic centimeters. The first state, state 1, is at this pressure that we do not know at this point, which we will just label for now to be P max. And we'll label that state 1. And that is connected to state 2 by way of a horizontal or isobaric process. And this is state 2. An isochoric process brings us to state 3. And we return to state 1 by way of an adiabatic process. And let's go ahead and label that. And we have a few more useful facts here. We're told that the temperature at point 2 is 600 Kelvin. And we're told that the volume at points 2 and 3 are 600 cubic centimeters. And at point 1, we're at 100 cubic centimeters. We also know the pressure at point 3 is 100 kilopascals. Great. We have one other important piece of information, and we're told that this cycle is a monatomic gas. Okie dokie. So let's get on with it here. We are going to be completing a first law table. So let's start by writing down the first law, which is Q plus W, here W being the work done on the gas, is equal to delta E thermal. And I'm going to go ahead and make those our column headings. And we're going to label our rows for not each state, but each process. So the first row will be labeled 1 to 2. The second row will be labeled 2 to 3. We have 3 to 1. And the last row will be the sum of each of these quantities. It's my advice that you put an X in the sum of the Q's here, because it is not useful, and you can run into trouble when it comes time to calculate the efficiency if that value is there looking at you. So we'll just put an X in there. And great. So what is the first step in solving a first law table? The first step is we try to identify any zeros that we can find in these processes. So are any of the quantities zero along any of these segments? Well, I like to start with the work. I think the work is the easiest. So we have zero work, or we have non-zero work from 1 to 2. We have an expanding gas, so it's actually negative work there. From 2 to 3, we have a vertical segment. The area under that curve is 0, and so we have 0 work going from from step 2 to step 3. Great. Any other zeros? Well, we know that we get the sum of the thermal energy around a loop is always 0, so this bottom corner, we always get a 0 there. And there's one more 0 that I can see in this chart, and that is by definition an adiabatic process, which is our process from 3 to 1, has 0 heat exchange with the environment, so Q is equal to 0 there. Next up is we're going to do the signs. So what can we identify the sign for? Now, thinking, let's do the work first, because I think the work is always the easiest. I said that already, and I mean it. So we have that as we go from 3 to 1, as we go from 1 to 2, let's start at the beginning. As we go from 1 to 2, we have a constant pressure process in which the gas is expanding, but the final volume is bigger than the initial volume. We're moving to the right. Anytime we're moving to the right, we have an expansion that is negative work done on the gas. So we're not smashing the gas is expanding from 1 to 2, so we're going to have negative work along 1 to 2. And from 2 to 3, the work is 0. From 3 to 1, we are smashing the gas there. We are compressing the gas. And so we're going to have a negative positive work from 1 to 2. We're smashing the gas, we're adding energy to that gas, so that is a positive work. All right, well, since we know we have positive work from 3 to 1 and we have 0 work, 0 heat along that same process, we have a 0 and we have a plus. That means that the sum of, or the change in the thermal energy must also be positive, because 0 plus a positive number has to equal another positive number. What else do we have here? Well, let's think about a process. Let's think about 1 to 2. We have a process here in which we're not changing the pressure. It means we're not pressing on the gas and we're not pulling on the gas, but it instead is, but even still, it is expanding, meaning, we have an increase in volume. So if we are not going to, by force and by might, expand or compress this gas, but instead we're just going to allow it to maintain a constant pressure and have a free piston that moves up and down. Remember that an isobaric process always involves a free piston that is free to move. How are we going to get that piston to move up? How are we going to get the gas to expand? Well, it's going to be through some contribution of heat. Is it ice or is it flame? Well, if it's heating up, right, if it's expanding, that's because we're adding energy to it and we're driving that expansion through heat. So we have a positive Q term for 1 to 2, and that also causes an increase in the temperature. So we're going to have a positive change in thermal energy here. Let's actually leave these blank for now, because I think we can arrive at that with a little more easier and intuitive approach if we look at 2 to 3. Now, those happen to be the signs for 1 to 2, but there's a little bit of guesswork there, or a little bit of familiarity that you have to have. But 2 to 3 is a little more straightforward. So from 2 to 3, we have a sealed volume. The work is actually 0. It's not just a constant pressure where we have a free piston, but we have a sealed volume. So the demonstration for a constant volume process is we have a sphere here. It's this ball that is completely sealed off. No gas can get in or out. The volume cannot expand or contract, and all it has is a meter or a gauge in it that tells us its pressure. And the way that we increase that pressure is, the way we would increase the pressure is by applying a flame, right? The only tool we have is heat. We can either apply a flame or ice, and certainly one is going to cause the temperature to go up and the other is going to cause the temperature to go down. So for an isochoric process, which is the vertical line, if we have a process which is going downward, this is an ice situation, or minus Q, or Q less than 0, I guess I should say, to be a little more explicit. This is how we would cause the pressure to drop if our only tool is heat, which is the case in an isochoric process. And consequently, or in contrast, if we have an increasing pressure at constant volume, that would be like a flame, and that would be Q bigger than 0. If the only tool you have is heat to manipulate the gas, then there's two possibilities, either ice or flame, and their corresponding relationships here. So I think that one is a little more explicit. So let's go ahead and fill out our signs there, because once we have the signs there, we're going to be able to draw some more conclusions about the other values. So we know that from 2 to 3, we have a downward isochoric process, which is one involving negative Q. And that means that we are also going to have a decrease in the thermal energy because the work is 0. Now, if we look at the sum of the thermal energy around the loop, we have some quantity minus another quantity plus another quantity is equal to 0. Can we draw any conclusions about the sign of delta E thermal from 1 to 2? I guess not explicitly, but it was worth investigating even so. But my argument before stands. If we think about how we perform an isobaric expansion, in an isobaric expansion, the demo for that is we have a glass tube with a ball here that is free to move up and down. This is our frictionless piston, and it's connected to a large reservoir of gas, which is just a bottle, right? A clear bottle here that's attached to it. And we want to cause that ball all on its own without applying any additional force to either go up or down, meaning expanding or compressing. And we're not going to apply any additional force. There is a fixed force or a fixed pressure that's provided by the mass of the ball and the weight of the air, the pressure of the air above. So if we want that ball to move up, that's going to be through the contribution of a flame right? That is going to be adding energy. This is a plus Q situation, which is also corresponds to a change or a plus increase in the thermal energy. So we'll say delta T is also greater than 0 for a constant pressure process when we add a flame Q. Now, if we have the ball going down, so this is for delta V greater than 0 is this situation here. If we have delta V less than 0, meaning we're smashing the gas, that is because we have lowered the temperature by, adding some version of ice, and we have delta T less than 0 for the case when the volume is decreasing. So in our particular situation, we have an expanding volume. We're going to get that through the application of heat and the corresponding increase in temperature that goes with it. All right, so now let's do the next step. We did the zeros and we did the signs. The next thing that I recommend you do is that we calculate the easy work. Okay, so how to do that? Do we have any easy work here? Well, certainly the work from 3 to 1 is not easy work because we want to calculate the area under the curve, and that involves an adiabatic curve. But from 1 to 2, calculating the work should be pretty straightforward. It's just the area of this rectangle minus the area of the rectangle is the work done on the gas. Now, we've already figured out the signs, which is nice. So we can just think about, when we're getting a number here, calculating the magnitude for each of these situations. And so the magnitude of the work from 1 to 2 is just going to be the area of that rectangle. I will keep the signs around just to be explicit, but the work from 1 to 2 is equal to minus P times delta V, which is equal to minus P times V final minus V initial, or we can call it P times V initial minus V final and kill the minus sign out in front if we like. The initial volume is this left-hand volume, 100 cubic centimeters, and the final volume is 600 cubic centimeters. So that is a change of 500 cubic centimeters, and so V initial minus V final is actually going to be minus 500 cubic centimeters. So this is going to be P times minus 500 times 10 to the minus 6 cubic meters, because there is 1,000,000 cubic meters in a cubic centimeter, and we want to be an SI unit, so we get joules out of this calculation. But we don't know the pressure. All we have is it's this P max at this point. So how are we going to figure out this pressure at point 1 or point 2? I'll just label it point 1. How are we going to figure out the pressure along this? Well, the only place that we do know the pressure is at point 3. So we need to link the pressure at point 3 to point 1, and those are linked through the adiabatic relationship. So let's go ahead and see what that looks like. Along an adiabat, 2 points that are connected by an adiabat, so in this case we have point 3 and point 1, and they're connected by an adiabat in between them. The way that these guys are linked is by the expression P 3 times V3 to the gamma power is equal to P1 times V1 to the gamma power, where gamma is the ratio of Cp and Cv, but it is also on our equation sheet here. So if we take a look at our equation sheet, and down at the bottom here, we have gamma for a monatomic gas. It's 1.67, and gamma for a diatomic gas is 1.4. In this case, we're going to choose the monatomic 1.67 because we were told it was, in fact, a monatomic gas that was completing this cycle on the PV diagram. So we're going to take gamma equals 1.67 for our calculation here. I'll just go ahead and write that down for now. Well, isn't that a little bit hard to read? Let's see if we can make that a slightly better yellow color. Maybe, yes, it's like school bus yellow over here, much better. Let's save that for later. All right. Great, so we are looking for the pressure number 3, that's our pressure number 1, that is our P max up here. And so let's go ahead and solve this for P1. We're going to get P1 is equal to P3 times V3 over V1, and that's all going to be raised to the gamma power, which is going to be equal to P3, which was our 100 kilopascals, that's 100 times 10 to the 3 pascals, times V3 over V1. Now, V1 is the smaller of the two volumes, and V3 is the larger of the two. Those have a ratio of 6 to 1. So this is just going to be 6 times, or to the power 1.67. That is dimensionless because this is the ratio of two volumes. That's going to give our pressure at 0.1. And if we plug this into our calculator, that's 100 times 10 to the plus 3 power times 6 to the power 1.67. And that is, gotta add some parentheses here in my calculation. Bear with me here a moment. 2,187 kilopascals. I didn't recognize that number, so I double-checked it, and it turns out I typed it into my calculator wrong. The correct answer is actually 1,993 kilopascals. So, thank you for that. And now we have the pressure at 0.1. So now we can go back to our work calculation down here, where we needed to know the pressure at 1 in order to calculate P times delta V. So the pressure now we know is 1,993 times 10 to the 3 pascals. And that's going to be multiplied times our minus 500 times 10 to the minus 6 cubic meters. And if we multiply these together, we get a total work done by the gas, or negative work done on the gas along that process 1 to 2, which is equal to, go ahead and plug this into my calculator, 1,993 E times 10 to the 3 pascals times 500 times 10 to the minus 6 cubic meters is 996, 997, I guess, kilojoules, excuse me, along that process. That's a minus sign here, so minus 997 kilojoules from the process. I think it's just joules. I don't know where I'm getting kilojoules here. Yeah, just joules. I thought, misreading my value here. Joules. Minus 997 joules. So let's go ahead and update our first law table with that value. The minus sign agrees from 1 to 2, so that's always a good check since we did the sign ahead of time. We're going to get minus 997, and I'm just going to write all units joules at the top of this table so I don't have to write a J in every box. Great. So does that allow us to calculate anything else? Not yet. Not yet. Is there any other work that we can easily calculate? I don't see any. That was our only geometric integral there. So looks like we're going to have to do the next step. And I recommend, if we calculate the easy work, the next thing to do is to calculate any values of delta E thermal that we can. And we're going to need to know the temperature at various points in order to do that. We have a temperature at 0.2. We can relate that either to the temperature at 0.3 or the temperature at 0.1. We have the pressure at both, so it should be pretty straightforward. So for that, well, let's just write it down. Let's do 2 to 3. Why not? So we know that for all processes, the change in the thermal energy is equal to NCV delta T. Regardless of the process, this is always true. The thermal energy only depends on the states, not on the process that you take to get there. And so we have the temperature at 0.2. We do need to calculate the temperature at 0.3 in order to solve this equation. So let's do that first. So we're going to have, anytime we want to relate two states, what we're going to do is write down the ideal gas law twice. So we're going to have P2 V2 is equal to nRT2. And similarly, we have P3 V3 is equal to nRT3. Next thing I like to do is erase the subscripts on the variables that are constant in connecting those two. So what do we have as constants here? Well, it's a constant volume process, that vertical line, so we can erase the subscript on the V. And we're looking for the change in the temperature, so we do that. We have the pressures at both points, so I think that is it. So we're going to solve for everything that has a subscript on one side of the equation, and everything without a subscript goes on the other side. So we're going to end up with P2 over T2 is equal to NR over V. From the first equation, and we also have P3 over T3 is equal to NR over V from the second equation, or P3 over T3 is equal to P2 over T2. We're looking for the temperature at state 3, So we're going to get that P3 over T2 is equal to, divided by P, excuse me, let's try this again. Trying to skip steps here. It never works out well. I got a phone call, which didn't help things at all. So we're looking here for T3. So I'm going to move that up over here, and then I got to invert this other ratio here. So we're going to have P3 over P2 times T2 is equal to T3. Great. So that's going to be equal to our pressure at state 3, which is our 100 kilopascals, divided by our pressure at state 2, which is our 1,993 kilopascals. And that's going to be times our temperature at point 2, which is the given 600 Kelvin. And if we plug this into our calculator, we are going to get 30.1 Kelvin. Cold. Great. So let's go ahead and drop that into our chart here. That would, or I guess that we don't have a chart for that here, but we can label it here on our diagram. We have 30.1 Kelvin here at state 3. Great. Now we can return to our thermal energy calculation. That's why we calculated this in the first place, right here. And so now we have the ability to calculate delta T. This is the change in the thermal energy from 2 to 3. That's what we're calculating here. And we know the temperatures at both state 2 and state 3. But we don't have the number of moles. So we're going to have to figure out the number of moles. Where can we do that? Well, in order to calculate the number of moles, we need P, V, and T. So we can do that at either state 2 or state 3. I'm going to choose state 2, no reason in particular. Let's go ahead and do that. So we have P2V2 is equal to nRT2. And we want to calculate n here, so let's just solve for it. N is equal to P2V2 over RT2, which is going to be equal to P2, which is our 1,993, I guess I didn't write it down when I should have over there. 1,993 kilopascals. I'm going to go ahead and label this on our diagram so we don't forget it. And that's in kilopascals, not to forget here. 1,993 times 10 to the 3 pascals times V2, which was our volume there, and it's the large volume, so that's going to be 600 times 10 to the minus 6 cubic meters, divided by R times T. R is 8.31 joules per mole Kelvin. And the temperature is 600 Kelvin. So plugging this into our calculator, we calculate the number of moles to be 0.238 moles. Gotta go ahead and write that on our chart as well. All right, now we are in a position to solve for the change in the thermal energy along that path to 3. I'm going to zoom in a little bit more just because we're running out of room here. So the change in the thermal energy along that path to 3 is equal to NCV delta T. Now CV is something that is also on the equation sheet. I can't remember if we already looked it up because I am recording this for a second take and may have already done that. I don't remember. So we'll just take a look again. We can see that the equation sheet does have values for both diatomic and monatomic gases. CV, 12.5 joules per mole Kelvin is what we're going to use for our monatomic gas. And notice that CP is not on here. If you have an equation involving CP or trying to solve a problem involving CP, we have to use this relationship, which is somewhere on here. Right here, CP is equal to CV plus R. So we can always take the CV value at 8.31 and get the value for CP. But we need CV in this case because we're calculating thermal energy, and thermal energy always uses CV regardless of the process. So we're going to get that the change in thermal energy along that process to 3, which is the isochoric process, is equal to N, which is 0.238 moles, times CV, which is 12.5 joules per mole Kelvin for a monatomic gas, times the change in the temperature, which is our final temperature is our 30.1 Kelvin, minus our initial temperature, which is at the top of that vertical segment, which was 600 Kelvin. So if we plug all of this into our calculator, we calculate that from 2 to 3, the change in the thermal energy is equal to minus 1,693 joules. Minus 1,693. Great. So we have a minus sign here. Does that match the sign that we had already deduced on our table? From 2 to 3, yeah, we do have a minus sign, and we said this was going to be minus 1,693 joules. And I'll rewrite the minus sign just so it is totally clear. Great. So what's next? Well, now that we know there's a minus 1693 here, we also get a minus 1693 in the Q box over here on the Q from 1 to, or excuse me, Q from 2 to 3 is also now determinable. And while we're getting close, we're not quite there. Even though we have 1, 2, 3, 4 boxes left, 5 boxes if we include the sum down here, I think that we're only going to have to do one more calculation. So we have a choice. We could use, let's go ahead and we'll use a Q equation, although we could calculate delta E thermal again. This would be the wiser choice because we can use the same equation that we've already been using, or we could use NCP delta T for Q. Let's use delta E thermal. I think it's just a better way to go. This one always, the same equation always applies for this column regardless of process, and so I think it's just a more rugged way of solving the problem. Now, before I say that, do we have the temperature at both 3 and 1? Oh, we don't have the temperature at 0.1, so that's going to require a little extra work. What about Q? Oh, we're going to need the change in temperature to calculate it by the Q method as well. So 6 one way, half a dozen another. Let's calculate the temperature then at 0.1. So how are we going to calculate the temperature at 0.1? Well, we need to relate some variables that we already have. Once again, I'm going to try and avoid the adiabatic process if I can, because it's a little nasty to deal with, but the constant pressure process is not so bad. We do have the temperature and the pressure at 0.2, and we have the pressure the pressure is unchanged at 0.1, and we have the volume at 0.1, so we can get the temperature at 0.1 because those are just linked by the ideal gas law there across 1 to 2. So let's go ahead and do that. So we're going to write down the ideal gas law twice. We have P1V1 is equal to nRT1, and we also have P2V2 is equal to nRT2. In this problem, it's the pressure that doesn't change. So in this segment, it's the pressure that doesn't change. So we can drop the subscripts on P, and now we can put everything that does have a subscript on one side of the equation, and on the other side, we can have things without the subscript. So we're going to have V1 over T1 is equal to NR over P. And similarly, we have V2 over T2 is equal to NR over P. And then we can equate these two, and we end up with V1 over T1 is equal to V2 over T2. Now we need to solve for, we're looking for the temperature at 0.1. So this is going to move up over here, and we're going to invert the fraction on the other side. So we end up with V1 over V2 times T2 is equal to the temperature that we're interested in, T1. The ratio of the volumes, well, V1 is the small volume of 100 cubic centimeters, and V2 is the volume 600 cubic centimeters. So this is going to be 1/6 times T2, which was our 600 Kelvin, is equal to T1, or T1 is a nice round 100 Kelvin. Great. Let's go ahead and put that on our chart, or our diagram here, so it's there if we need it. This is 100 Kelvin. And we can now calculate the change in the thermal energy from 1 to 2 using that same expression. Oh, you know where I'm going to do that? I'm going to zoom in here to this box because that will be nice and tidy. So the change in the thermal energy from 1 to 2 is going to be the same expression as it is because it's independent of the process, NCV times delta T. And we know N now, the number of moles doesn't change, so this is going to be 0.238 moles times CV, which is still 12.5 joules per mole Kelvin, times delta T, which is going to be our final temperature is that 600 Kelvin on the right minus our initial temperature, which is our 100 Kelvin here on the left. And so we're move across here. We're looking at the constant pressure process. And so now we can just plug this into our calculator and see what we get. And so that is going to be 0.238 times 12.5 times 500. And that is 1,488 joules. So the change in the thermal energy along 1 to 2 is equal to a plus 1,488 joules. Let's see if the sign agrees with what we discerned earlier. It sure does. We have a plus sign here. So this is going to be plus 1,488. All right, so now we can figure out quite a few additional values here. We have that the sum around the loop has to be 0. So 1488 minus 1693 plus what's left is going to have to equal 0. So that is 305 joules there for this process. And now we know this is 305. We have to sum across the row because Q plus W equals delta E thermal. So 0 plus blank is equal to 305. So this is also 305 joules. And then we have I'm sorry, I made another transcription error here. This is 205 joules, another calculator error, not 305. This is also 205 then. We conclude. So now we can find out what the net work done by the gas, or the net negative work, is around the whole cycle. So that's going to be 997 minus 205. So it's going to be minus 792 joules is the net work done on the gas during a cycle, or you get roughly 800 joules more out of the process than you put into it. And we have one more box, which is this plus Q term in the upper left-hand corner. And what do we subtract 997 from to get 1488? And what we do is 1488 plus 997 is 2,485 joules. Phew. And that should be plus, right? We have a plus sign there, and so we are in agreement. Great. So there is our first law table and all the steps there to calculate the values in there to propagate that first law table. And that one involving an adiabatic process. This PV to the gamma power is, we don't write down the ideal gas law twice for an adiabat. Instead, we write down P1 V1 to the gamma and P2 V2 to the gamma and set those equal to one another. It actually does come from the ideal gas law, but at any rate, I hope that was a useful explanation for you guys, and I'll see you in the next one. Farewell.